All right, let's give these questions a go. So for my first question, we have an alcohol, and we're converting it to an OTS. So for this portion of the chapter, there was quite a bit of memorization, so it's up to you guys to know that that stands for tosol, which is one of our superleaving groups. So we've got to get that attached there. And for the tosol, that's the one that has sulfur, double bond O, and then it's based on toluene, which is a benzene with a methyl coming off of it. So that's basically what I'm trying to attach. Again, you are responsible for the mechanism of how that will attach, but if it's a question like this and you just have to fill in the conditions, you are welcome to use the shorthands. So in this case, a shorthand for the tosol is TS, but in order for the mechanism to work, I have to have a leaving group attached. So that would be like tosyl chloride. And the other important component is that we have pyridine present. Again, you can draw the structure or use the shorthand of PYR to represent pyridine. That serves as both of our solvent and also a weak base in the mechanism. So that's the first one. Second one, we're doing a similar reaction where we are converting to a superleaving group, and this one is mesyl. So the core part is the same, it's a sulfonate ester, the difference being I just have a methyl group on the end as compared to what we would see from toluene. So that means I'm doing a mesyl conversion. And again, because I'm filling in conditions, you're welcome to use the shorthand. Just for fun, to be kind of matching in this one, I'm going to write out the structure. So I'm going to have the mesyl part, and then I need that leaving group attached. So that would be our chloride. And why not? Let's draw pyridine as well. So again, you're welcome to use either one. You could draw it like that, or you could write mesyl chloride and PYR, and it all means the same thing. Now our last one's a little bit different. We're asked to fill in the product, and we've been given a 3-step condition. This one is pure memorization, so you are not responsible for the mechanism of this one. But we do need to know what these things stand for. So TBDMSCl, which stands for T-butyl dimethyl silochloride. I know, mouthful. You could also know based on the structure, so make sure you flip back and take a look at what the structure is for this. And when we use it is for strictly one purpose, which is our protecting groups. And in this course, we are only doing protecting groups of alcohols. So basically the first step here is going to protect that alcohol so it's no longer reactive. So that's step 1. Step 2, we have T-butoxide, which is a very strong and bulky base. And we also have heat. So now the question is, if I ignore that alcohol, what's going to happen with the rest of the molecule? And in the rest of the molecule, I've got another leaving group, or another functional group, which is bromine, which can act as a leaving group. So now I'm just going to straight up ignore that alcohol, assume he's not reactive, and just ask myself, okay, between this and this, what's the most likely reaction? T-butoxide exclusively does E2. That is all he is good for, even at a primary center, which is the hardest place to do an E2 because SN2 is more favorable. But I have that big bulky base. I've got the heat to help back up my answer here. So my decision is that I'm going to be doing an E2 at that carbon center, which is bearing the leaving group. So that's the mechanism I'm going to be doing. And then in step 3, we have tetrabutyl ammonium fluoride, which you might recall from earlier is a deprotecting agent. So he's going to deprotect my alcohol and put it back into its original form that we saw on the left-hand side. So get rid of that protecting group. So really, for this, as long as you recognize you're protecting and deprotecting and don't get bogged down in those details, all you really need to figure out is what's the E2 product, and the alcohol is going to be the same in the product as it is in the starting material. So I'm going to do an E2 between my alpha and beta carbons, which means my double bond is going to form there. So just make sure you count your carbons when you go to draw your answer. I've got the alcohol, which I haven't touched because he was protected, I reacted, and then I deprotected. So bump, 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 bump. That should be the right number of carbons. Let's check. 1, 2, 3, 4. 1, 2, 3, 4. Good. I'm going to lose the bromine in the process to form that double bond, and it forms between carbon 3 and 4. That's kind of messy. Bam. So there we go. That would be the final product of that reaction, which involves a protection and deprotection. Why is it necessary to protect and deprotect? That's an excellent thing you should be asking yourself. If you look at your starting material with that alcohol, and if I just threw this whole molecule in with my conditions of step 2, the T-butoxide, because he's such a strong base, he would rip the hydrogen off that alcohol prior to the E2 happening, or at the very least, I would get a mixture where sometimes it happens as well. So we want to make sure that he doesn't interfere so I can keep that hydrogen there the whole time, and then I can get my E2 product. So that's an example of protecting, deprotecting, as well as our super leaving groups. So the next little section we're going to cover is one of my favorites, and actually the last topic in this module, and it involves something called epoxides. And what an epoxide is a cyclic ether. So if I asked you to draw the generic form of an ether, you should come up with that. So an oxygen bound to 2 carbons. And to make it an epoxide, the 2 carbons just happen to be attached to each other, which makes it cyclic. I'm going to strictly call them epoxides, but technically it's an oxirane for the IUPAC name, or ethylene oxide. So a couple different ways we can make epoxides. The first one we're going to talk about is something using peroxy acid. And the term peroxy acid comes from 2 words we actually know already, peroxide, and the acid is from a carboxylic acid. So if I asked you to draw each of those things, whoops, that's not how you spell, you would probably come up with a peroxide looking something like this. So 2 oxygens attached to each other, and a carboxylic acid having a carbonyl OH coming off of it. So what a peroxy acid is the 2 of those combined. It looks like a carboxylic acid, but it has an extra oxygen in it. So it's an OOH with a carbonyl on it as well. And there's all different types of peroxy acids you can use. My personal favorite is this R group here, looks like this. So a benzene with a chlorine coming off of it. And it's a really common one that we use to make epoxides, and it's called metachloroperoxybenzoic acid, which is a mouthful. So instead, we call it McBAPA. And you are welcome to make fun of me for that, but that is much quicker to say. So McBAPA from here on out. And you're welcome to use that shorthand, but if I draw the structure, you also have to recognize what it is and what it does. This is the only time we use a peroxy acid, so if you see one, again, this is what makes it a peroxy acid on the right. So if you see this, regardless of what's in red there, whatever's coming off of it, you got a peroxy acid, and he makes epoxides. And if I showed you this reaction here and asked you what type of reaction it was, if you look at your starting material, you've got an alkene, and in the end, I've got an epoxide. So the type of reaction would be an addition. I'm adding a single oxygen across the double bond here, and we're going to look at how that works a bit. This slide goes over the mechanism of the epoxide formation using a peroxy acid. I'm not making you responsible for it, so I'm not going to ask you to replicate this particular mechanism, but I just think it's kind of neat, so I wanted to show you what it looks like. It's concerted, so everything's happening in one step here, which is why we've got a ton of arrows happening all at once. And it's a syn addition, so the oxygen's adding to the same side of that double bond, which makes sense. If you recall before, when we've done this type of reaction, we're not going to have the oxygen add to the top and bottom, because then the bonds would be crazy, like the angles would not make sense. In the process, our alkene comes up to the peroxy acid and donates its electrons to one of the oxygens. This bond, which again is 2 electrons, donates back, which gets me the second bond to oxygen. I need to break this oxygen-oxygen, so the peroxide bond, which is ultimately going to form a pi bond here. And then this pi bond is going to pick up this hydrogen to ultimately give me a carboxylic acid in the end. So it's kind of fun, but there's a lot going on. If you just keep in mind that you're forming a carboxylic acid along with your epoxides, then it's not so bad to follow the arrows. Keeping in mind that when the alkene comes up to the peroxy acid, it could attack top or bottom, which means I will get a mixture of products here, so you do have to watch out for your chirality. As we said on the previous slide, this is a concerted reaction, and it does proceed with a syn addition. So adding across the double bond, the oxygen is going to be bound the same way to those 2 carbons. So the easiest way to do this, hopefully this is ringing a little bit of a bell from when we did the bromine additions. I would personally take my alkene, make it three-dimensional first. So here's my alkene. I'm going to take that and I'm going to make it three-dimensional. So I'm going to wedge both those methyls, dash the hydrogens that are coming off there as well. And then I'm going to add my oxygen either on top in the plane or on the bottom in the plane. So I don't have to worry about dash wedge. What I'm adding is in the plane, everything else is dash wedge. So if I follow along with the two oxygens adding top or bottom, I would get these two possible scenarios. But what's interesting with this example is, yes, I've created chiral centers, but they have the same groups attached. And if we ever do that, the thing we have to watch for is meso. So anytime you make a chiral center, assign your RS. In this case, I have RS. In this case, I have SR. If you have one R and one S, then you should be thinking meso. Check and see, do I have the same functional groups coming off there? Do I have a plane of symmetry? So hopefully you can see that we do have a plane of symmetry running down the center of these guys. If I were to flip this guy 180, it would be the same thing. So the answer for this particular question, starting from my cis-butene, is I only get one product. Not two, but draw both paths and then decide if they're the same or not. Whereas if I have the trans-2-butene with the exact same conditions, I will get a mixture. I will get RRSS. These are not the same thing. How are they related? If all chiral centers switch, what do I call those? Enantiomers. So I get a pair of enantiomers. If I get a set of enantiomers, a 50-50 mixture, what do we call that? Racemic. And is that optically active? No. Just a bit of review. Wanted to throw that in there. So we have another way that we can make epoxides. It's a couple steps versus the one, but I really like it because it actually is derived using things you already know. So how it goes down is, first of all, we're going to do an addition from an alkene, but we're not directly going to add oxygen. We're going to do this one, bromine and water. And if you recall, that one is called the halohydrin, which results in a bromine and an OH being added anti to each other. Keep in mind, there's also an enantiomer. I'm just showing the one to make it simpler, but I would get a mixture of products from that first step here. They do an anti-addition, so my bromine is on the opposite side as my OH. And then if I were to add in some base, potentially hydroxide, that's equilibrating, or what if I said one equivalent of NaH, for example? Very, very strong base. The base is going to take off our hydrogen using just acid-base reaction. So if I remove that hydrogen, I get an alkoxide. What can an alkoxide act as? A nucleophile or base. And within this same molecule, I actually have an electrophile and a leaving group. So this nucleophile can attack the electrophile, which is adjacent to it, and kick out the leaving group. Pretty cool, right? Yes, very cool. And the reason this guy has to be an anti-addition is because in this mechanism, my nucleophile attacking my electrophile, kicking out my leaving group, that strong nucleophile is that SN1 or SN2. That's an SN2. And for SN2, how does the nucleophile have to be positioned relative to the leaving group? Backside attack. So for it to do a backside attack, inversion to take place, we need that oxygen to be the opposite side of the bromine. So pretty cool, 2 steps, gets us to our epoxide, or you can use the peroxy acid. So please be aware of both. You are completely responsible for these mechanisms because this is all review. We have done each of these mechanisms on their own. The first one is an addition. The next one is acid base / SN2. So keep that in mind, and that's how we get an epoxide. Once we have the epoxide, it's not entirely stable. True, it doesn't have charge, which is a good indicator of stability. So because it's not charged, I don't immediately see it as unstable. But if you recall back in Module 4, we talked about strain. And an ideal molecule that has no strain in terms of rings is a 6-membered ring. So cyclohexane had no ring strain, which was a combination of angle and torsional strain. So if we're having a 6-membered ring being no strain and we're on a 3-membered ring, that definitely has strain. So if you want to see that in the real life, just try and build this with your model kit and you will basically be breaking your model kit. You'll break some of the bonds. It is going to be strained. It doesn't want to make that ring. We've seen a very similar thing before in Module 8. When we were adding bromine, we saw something like this. It was an intermediate, definitely not a product, but very unstable for a couple reasons. Because it's a 3-membered ring and because it has that positive charge. So just like this one, we're going to be able to do some chemistry that breaks open that ring. So there's a couple different ways we can open the epoxides. So this reaction of epoxides is really opening epoxides. And there's 2 conditions we can use, and they do slightly different things, so it's important to distinguish between them. There's acid catalyzed opening, which involves dilute aqueous acid. And if I asked you what type of acid this was, H2SO4, you should probably tell me it is, nope, not polar, it is strong and it is non-nucleophilic. And that's important because we're going to need a nucleophile in the reaction and I don't want it to be coming from my acid. So a non-nucleophilic acid and then water or some other oxygen with a lone pair. So we could use methanol or ethanol, something along those lines, but those will do slightly different things. So basically, I want an oxygen with lone pairs to act as my nucleophile. Only water will give me the reaction products I've listed here, and we'll see why in the mechanism. Overall, what this gives me is anti. So the 2 oxygens I'm adding on here are anti to each other. And if you backtrack to the alkene I would have started with in this case, my alkene would have looked like this. So our alkene would start like that. We would make the epoxide using peroxy acid maybe. Once we have that epoxide, I can open it up and get an anti-diol, which is in contrast to permanganate that we saw in Module 8, which gives the syn-diol. So the mechanism for this is really fun. First of all, I want to recognize where my acid came from here. So my conditions were H2SO4 water, which you may recall means I actually have H3O+. This is such a strong acid, he's going to give away that proton to the water and form hydronium. So in the mechanism, what I'm going to be using is either hydronium or water, never H2SO4, because that's pretty much gone at this point. So the first thing that's going to happen is we're going to look at our epoxide and think, okay, what could this do? It's got a lone pair on an oxygen, which we've continually been using as either a nucleophile or base. And if I asked you what H3O+ is, hopefully you would tell me that's an acid. So the most likely combination here is an acid-base reaction because I have a strong acid where that lone pair picks up a proton and forms a positive charge. This positive charge sits on my oxygen atom, and hopefully this reminds you of something we've done before, like this. If I showed you that alcohol and said I had H+, he would gain a proton and become this. Why would I do that? Think back, Module 7. Why would I protonate an alcohol? It was to make this into a leaving group. Exact same principle with the epoxides. I protonate it to make it into an even better leaving group. And once I've done that, this behaves just like if I had the bromine there. So think back to the mechanism you did before, where I had a bromine with a positive there. This behaves exactly the same way. So if I was doing the halohydrin and I presented you with that starting material and we got to this point here and I asked you to bring in the water, you would have a choice as to which carbon you would attack, A or B. And if you recall from Module 8, we decided we would be attacking HB, or carbon B. Do you remember why? There was a good reason behind it, and it wasn't sterics. Carbon B is the harder one to get to, but that is the better option for that water molecule because this carbon more resembles a carbocation. It has more of the positive charge. This bond is weaker. It's barely attached. So that's what the water's most attracted to, because if I asked you if water was a strong nucleophile, you would tell me it's not. That's a weak nucleophile. And weak nucleophiles are looking for the most positive center, the most attractive center. So just like the halohydrin, it will preferentially attack the carbon that's the more substituted. Exact same thing with acid-catalyzed epoxide opening. It behaves exactly the same way. The oxygen is still my weak nucleophile, but it is going to attack this electrophile, and it's going to kick out that bond as my leaving group. And it preferentially attacks the carbon that is more substituted because that more resembles a carbocation. And the weak nucleophile needs something super attractive to attack. Okay, big explanation. Hopefully that makes sense. Once my nucleophile attacks that carbon, though, I'm not done because I've made a bond here between the oxygen and the carbon, which results in a positive charge on this oxygen. And that's an easy fix, just like we did with the other alcohol chemistry. I'm going to bring in a weak base, in this case just more water, to deprotonate that acid and get me to my diol. So the two oxygens are on opposite sides. They are anti to each other because when the water comes in, let's go first this. When this water comes in to attack, it does a backside attack. It comes in from the opposite side because this guy is up. That's taking up a lot of space. This guy is going to be back, which is why he's dashed. Exactly like we did in Module 8. So this, we're going to think of like an SN2. And keep in mind this is acid-catalyzed epoxide opening, which means I'm starting with an acid up here, H3O+, and in the end I have regenerated that same acid. When I introduced this topic of opening up epoxides using acid, I said that we don't have to use water as the solvent. I could use something else like methanol or ethanol, but I won't get the same product from it. So keep in mind, if I'm using methanol or ethanol to be my nucleophile, then when he comes into attack, I will get him attached and the carbon is still there. You don't just lose that carbon. So let's do a little practice of the mechanism here. When I combine these two things, I'm really going to have protonated methanol, which is just the equivalent of hydronium. That's a nice strong acid. My epoxide can act as a base. So he's going to pick up that hydrogen there and give me a protonated version of my epoxide. Oops, one lone pair. Reason we do that is to make him into a much better leaving group, which I need to do because my nucleophile here is crappy. It's water, methanol, ethanol, whichever. It's neutral. So he's weak. He's going to come into attack. And in this example, I don't have a difference between the two carbons he could attack. Either one are equally substituted. So I need to show both. So here, let's show attacking the right one. And that's going to give me, oops, let's make that bond better. Oxygen, oxygen, hydrogen. The methyls are still there, haven't done anything to those. And these are still attached to my nucleophile because I didn't do anything to them. There's no reason that carbon is going anywhere. Am I done? Nope. Still have a positive charge. Got to fix that. So what am I going to bring in to deprotonate? Not water. Don't add water. You don't have water there. You didn't make water. You can't just put water in. What I do have is methanol. So another molecule of methanol is going to act as my base. He'll take that hydrogen to deprotonate him and get me to that version. And then I draw the exact same thing from a second path over here to get to that version. So draw that one as well. Make sure you can see both pathways. They would form in equal amounts. There's no reason one would form over the other. But again, this CH3 is still present in both. That can't just fall off. If that's your nucleophile, that needs to show up in the product. Once again, this is just going over the theory behind the selectivity. So for the acid-catalyzed ring opening, it has the selectivity that's SN1-like in that my weak nucleophile will preferentially attack the carbon that is most substituted because it more resembles a carbocation. If I have to put the positive charge somewhere and I have a choice between A and B, I would choose to put the positive charge on A because it handles it better. And the nucleophile senses that. The nucleophile coming up to the molecule sees which carbon is more positive, and that's the one it wants to attack. So it would attack HA, and we would get the intermediate that looks like this. Keeping in mind, I would have to deprotonate to get to my final product. So, reiterating, this has the exact same selectivity as the halohydrin. So where you have that bromine, three-membered ring, that's positive. And then if I had an unsymmetrical one, the nucleophile, in this case the water, would attack that carbon preferentially. So, same idea. As I said, there are two ways we can open the epoxides. So far we've covered the acid-catalyzed ring opening. The next up is the base-catalyzed ring opening, and they do slightly different things, which is why it's important to distinguish them by their conditions. So in this case, we're starting with our same epoxide starting material, but instead of having acid, I'm going to have a base present. So for example, sodium hydroxide or sodium methoxide or ethoxide. Also works with alkoxides, so keep that in mind as well. But they wouldn't lead to these products. They would lead to something different. Let's not do an arrow, that's confusing. So if I want to look at the mechanism of this, it's going to be a little bit different than the acid catalyzed. So here we're going to deal with negative charges as opposed to positive charges, which means the selectivity is different. One of the big differences in the mechanism is the first step. So with the acid catalyzed ring opening, the first thing I do is protonate the epoxide. So it would add a proton here in my first step of acid catalyzed opening. With base catalyzed opening, you have to think about what your nucleophile is. So if I have an alkoxide or sodium hydroxide, this is my nucleophile / base. And if I asked you, is that a strong nucleophile or a weak nucleophile? You should tell me that's strong. It has a full negative charge. What that means for the reactivity is it doesn't have to wait for a carbocation or something like a carbocation. It will initiate an attack. So the strong nucleophile is capable of attacking without first protonating the oxygen. And because of that, it behaves very much like an SN2. This strong nucleophile is going to attack the electrophile, and again we have a choice between A and B. For acid catalyzed opening, we were attacking B. With base catalyzed opening, we're attacking A. What's the difference? Well, for this strong nucleophile, he doesn't need to have a very attractive carbon to attack. He needs to have an accessible carbon. So the argument here is going to be sterics. He's in a rush to give away those electrons. He's just looking for the carbon that is the easiest to get to. So carbon A is the easier one to attack. That's the one he chooses. You might be questioning something here, because if this guy attacks and I break that bond up to that oxygen, the result is an O negative. And this is the very first time that we're kicking out an oxygen with a negative. Why is that a bad thing? That's not stable. So up until now, we've never kicked out oxygen negative as a leaving group, right? If I showed you an alcohol and said, is that a leaving group? You would tell me no, that's not a leaving group. So what's the difference? Why am I allowed to kick out O minus here, but I'm not here? The three-membered ring. So here, yes, I am kicking out an O minus and that is bad, but I'm breaking that ring strain. So there is an energy payoff that's associated with opening an epoxide that I don't get just kicking out a hydroxide. So that's why it's allowed. We're under base conditions, which means we're allowed to be creating some negative charges. And because I'm opening up that ring, I'm avoiding that ring strain and I get some payoff that way. So base goes for the less sterically crowded. So this is less crowded. That's why he attacks there. Once again, it's a backside attack, which means it's like an SN2. And the oxygen coming in, he came in from behind because the one that was already attached was on top. And we have to get them on opposite sides, otherwise it can't physically fit in there. So I've kicked out that O-, which is not great, but I got the ring strain relieved, so that's good. We're not done because I do have a charge there I have to fix. So something that could happen here is then an acid workup to make sure all the negative charges are neutralized. But in this case, we're going to allow to use just a solvent to gain that hydrogen. If I wrote acid workup, you're welcome to use the acid instead. But in this case, because it's in equilibrium and we've got loads of solvent, he would be in excess. I would accept him taking off that hydrogen in order to get the neutral charge here as well. So the products look very similar between acid and base catalyzed opening, but the selectivity is different and the mechanisms are different. So hopefully that makes a bit of sense. If you have some questions, don't hesitate to contact me, but do lots of practice and make sure you understand those mechanisms well. It is called base catalyzed because in the end, I have regenerated my base. So I had a base to start here, and I've regenerated it at the end. So this is a great slide that kind of does a summary of our acid and base openings for the epoxides and noting the different conditions and the selectivity involved. In the top case is our acid catalyzed opening, and I know that because I have positive charges throughout, and my base catalyzed, I have negative charges throughout. I also know because of selectivity. So in the first one, there would have been a step before this to protonate. So I would need to know what acid I'm using, but I would protonate that epoxide first to make it into a better leaving group. Why do I have to do that? Because I have a weak nucleophile. And a weak nucleophile requires a really good electrophile. Note which way it's attacking. He's attacking the more substituted, and that's because it more resembles a carbocation. And he's looking for the most attractive site. This is electronics that went out. Once he attacks, he's going to end up with a positive charge because he was neutral, which would mean a deprotonation step here. Can't spell. Deprotonate my nucleophile to get from here to here, because again, the nucleophile would have been water or methanol or something like that. In the base catalyzed version, we have no protonation step to begin with because I have a strong nucleophile that will attack my weak electrophile, but we do get the payoff of breaking open the epoxide and losing that ring strain, which is why we can get away with it. My strong nucleophile is going to react based on sterics. This is the least crowded carbon, which is why he attacks there preferentially. And then I don't have to deprotonate because he's already going to be neutral. He came in as negative, but I will have to protonate the oxygen because I kicked him out as negative. So I would need a proton source, typically using the solvent / nucleophile in order to gain that proton to get to my final product. So please understand the differences between the two. Keep in mind with acid catalyzed, I'm always going to have positive charges. With base catalyzed, I'm going to have negative charges. Just a little recap and connection back to something we've done before. You've been able to make a diol way back in Module 8, and we did it using KMNO4, NaOH, water, and cold conditions, or there was another version as well. Maybe you take a little refresher on that one. They both worked the same way, where they had two oxygens, two OHs coming from the same molecule, in this case the MnO4, and it added in a syn fashion. So the two oxygens added to the same side of the alkene because they were coming from the same molecule. We now have a new way of forming a diol. It is in 2 steps, and it involves first making an epoxide and then opening the epoxide. And if I open the epoxide using water as my nucleophile / base, then I will end up with a diol. If I use methanol or ethanol, then I won't get an actual diol. I would get alcohol on one side and a ether on the other side by the same mechanism. So we now have 2 different ways of making diols, and one does a syn and the other one ultimately is an anti. It just takes multiple steps to get there. So please keep that in mind for the stereochemistry going forward. It's very easy to mix these 2 up. So for multi-step synthesis, you have to keep in mind the stereochem and work it out completely. Congratulations, you have finished Module 10. So recap on what we covered in this module and what you're responsible for. First thing we were covering was a bit of review from the earlier chapters or modules where we did alcohols, so keep that in mind. In terms of reactions, we did the alcohol conversion using PBr3. Yes, you are responsible for that mechanism, so if you know the mechanism, you'll understand why the stereochem involves inversion. We then did the synthesis of sulfonate esters, which again was to make this, so they both make alcohols into good or super leaving groups. There was retention in terms of the bond to the oxygen. And yes, you are responsible for the mechanism, so you'll know why there's retention by looking at the mechanism. The next one we did was not technically something new, we just put a name on it. So the Williamson ether synthesis involves making ethers via a SN2 reaction. So it does have inversion because it's just an SN2. Then we did the synthesis of silyl ethers, which was for protecting groups. So these two things are our protecting groups. Specifically, we use them to protect alcohols. So the first two was trying to make the alcohols into good leaving groups, and then silyl ethers was to make it into a crappy leaving group and not acidic anymore. So we had to do the synthesis of the silyl ethers and then the deprotection. So this first one we would call protection, and the second one is deprotection. You are responsible for the two conditions involved with those, but you are not responsible for the mechanism. So that would be more synthesis, so you have to memorize those. Then we made making epoxides, and I said you aren't responsible for the peroxyacid version, which is this one, although I do have it in the slides. You are responsible if it's doing it via the intramolecular SN2, which was the bromine water in the first step, and then the opening. Oh, no, sorry. We're not opening yet. So the bromine water to get the bromine and OH attached, and then base, like one equivalent of NaH or NaOH to be weaker. And that would make our epoxide, and yes, you're responsible for the mechanism of those. Both the addition, which was the first step, that was our addition, and then this was acid base, and then SN2. So, yep, responsible for the mechanism of that. Then we did my favorite ones, which is the opening of epoxides. Two different versions, acid and base catalyzed. You are responsible for the mechanisms involved with those and the selectivity because they are different. So have fun, do lots of practice, because that's how you get good at chemistry.